Hello everyone, Chapter 2. This is Chapter 2 of our calculus book. It's our first section of actual calculus. Limits and continuity, Section 2.1, Rates of Change in Limits. I would recommend clicking on these links. They will also be up on Google Classroom for you to check out these videos and read through this brief history of what calculus is, how it started. There's another link down here to an interesting video about Sir Isaac Newton and Baron Gottfried Wilhelm Leibniz. Alright, and then read what is a limit, which leads us into the definition of a limit and then actually calculating limits. So find the limit as x approaches 2 of the equation x squared plus 1. Now, I've provided a graph. That means as x gets closer and closer to the 2 from the left and from the right, what is the function getting closer and closer to? Well, this function is smooth and continuous, which is very important in calculus. Means as I draw it, I don't ever need to take my writing utensil off of the paper, and so that's the continuous piece. The smooth piece means there's no jagged sharp turns or edges or cusps at all. So because this is smooth and continuous, we can do what we call direct substitution. So, or you can look at the graph and say, well, at x equals 2, we're sitting up here at y equals, or f of x equals 5. Because this is continuous, the function's value and the limit are the same. Limit as x approaches 2 of x squared plus 1 equals 5. Okay? And again, we can use direct substitution to put the 2 in here. 2 squared is 4 plus 1 is 5. Example 2. Here's an example where direct substitution doesn't work. We have to look at the graph and see what's going on. We've got a piecewise function. This is not smooth and continuous because we've got a hole, and then we have a function value that is above the hole. But as we look at this graph approaching 2 from the left and from the right, from the left and from the right, we are approaching the same location, the same value, which is right here at positive 2. So even though the function value is 3 when x is 2, the limit's value is 2 when x is 2. So limit as x approaches 2 of f of x, I'm not going to rewrite the whole piecewise function, equals 2. Again, because from the left and from the right, we're both approaching the same location. Example 3. Again, because we are dealing with something that if I were to graph it, would be smooth and continuous. Now, how do I know it's smooth and continuous? Because it's a polynomial. I know what polynomials look like. We've graphed polynomials for a long time in your mathematical career. So I know it's smooth and continuous. So I can do direct substitution. Okay. We also can do the limit of the sums is the sum of the limits. The difference of the sums, the difference of the limits is different. The difference of the limits can also be done, sudden differences. So I can rewrite limit as x approaches negative 1 of x squared plus 6x minus 9 equals. Now, I'm only going to show you this one time to make an illustration. You do not do this every single time you do a problem. This can be broken up into the limit as x approaches negative 1 of x squared plus the limit as x approaches negative 1 of 6x minus 9. Again, this is smooth and continuous. Direct substitution. Negative 1 squared is 1 plus 6 times negative 1, negative 6 minus 9. I do the arithmetic, I end up with negative 14 for the answer to example 3. Example 4, we do the same thing. Limit as x approaches negative 3, x squared plus 4x plus 3 over x minus 3 becomes the limit of the numerator as x approaches negative 3, x squared plus 4x plus 3 divided by the limit of the denominator. Of x minus 3. I can break the numerator up just like I did in example 3. Now I'm not going to take just like I did in example 3. I'm not going to take the time to actually write out each and every single limit. Okay, but that's in reality that's what's happening. But I'm going to write negative 3 squared, doing the direct substitution now, plus 4 times negative 3 plus 3 over negative 3 minus 3. Negative 3 squared, 9 minus 12 plus 3 over negative 6. 9 minus 12 is negative 3 plus 3 is 0 over negative 6, which is 0. Okay. Now, what this next section is telling us is that polynomials, you can do direct substitution. Okay? Polynomials, you can do direct substitution, which is what we just did in the previous few problems. And here's where we get our sum and difference rules. The limit of the sums is the sum of the limits. The limit of the difference is the difference of the limits. So on and so forth. Product rule, the limit of the product is the product of the limits. Constant multiple rule. If you have a constant out in front of a function, then you take the limit of that function and multiply it by the constant. The limit of the quotient is the quotient of the limits as long as the denominator's limit does not equal 0. And then we have a power rule function. Okay? The limit of a function raised to a power is, the limit of a function that is raised to a power is equal to the limit of the function raised to that power, as long as that power is a real number. So, example 5. We can go straight to direct substitution. 2 squared plus 2 times 2 plus 4 over 2 plus 2. 4 plus 4 plus 4 over 4 equals 12 over 4, which is equal to 3. So example 5's answer is 3. The limit of that function is 3. Example 6, just taking a look at the graph. Now I'm actually showing you the graph here. Okay, I'm not asking you to do anything with that other than being able to see this graph. Okay, what I want you to do next is, what is the limit as x approaches 0 sine of x over x? I can't use direct substitution here. This would be sine of 0 over 0. We can't have anything over 0. Okay? We can never divide by 0. That's why there's a hole in the function here at 0. It's undefined at 0. Okay? So I can't do direct substitution. But if we look at the graph, as we approach 0 from the left, and as we approach 0 from the right, they are both going to the same value. So what value are they both going to? They're both going to 1. That's something that you're going to want to memorize. The limit as x approaches 0 of sine of x over x equals 1. Something to memorize. Example 7. Again, I can't do direct substitution. I can't put a 0 in the denominator, so I can't do direct substitution. But I can look at the graph. Graphically, as I approach 0 from the left, and as I approach 0 from the right, they're both going to the same value. So graphically, as an ALY, we get the limit as x approaches 0, tangent of x over x equals 1. Again, okay? Algebraically, we can actually solve this one. So even though we can't do direct substitution, we can still solve this using what we know from example 6. Okay, so algebraically or analytically. We have the limit as x approaches 0, tangent of x over x. I can rewrite this equals the limit as x approaches 0 of 1 over x times tangent of x. I can continue rewriting this because we know tangent is sine over cosine. Limit as x approaches 0, 1 over x times sine of x over cosine of x. I can rewrite this again because sine times 1, I can move the sine of x over the x instead of over the cosine, which is what I'm going to do. So now I have the limit as x approaches 0 of sine of x over x times 1 over cosine of x. Now, why did I do that? I did that because of the rule that we have. Back here, rule number 3 here, product rule. The limit of the product is the product of the limits, which means I can separate these into 2 separate limits. So I'm going to come back up top here, draw an arrow to where I'm continuing. So I now have the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over cosine x. I don't need the parentheses. We know what this is from example 6. I said something that you want to memorize, right? That equals 1 times. I can do direct substitution here because the cosine of 0 is not 0. Okay, cosine of 0 is not 0, so I'm not going to be getting a 0 in the denominator. Direct substitution is going to be 1 over cosine of 0. Just so that you see where that comes from. Equals 1 times 1 over cosine of 0 is 1. 1 times 1 divided by 1 is 1. Same result that we got graphically. Okay. Introduction to limits. We're going to do that in class. What does it look like? Let me pause the video and pull that up. So here is the example 1 on the worksheet. I'm going to make this full screen. So example 1, determine the limits for each part of the function graphed below. So the limit as x approaches infinity of f of x. So here we have a graph. As x is going out to infinity, what is the graph doing? The graph's coming down and going out to the right. What is it getting closer and closer to? It's getting closer and closer to the x-axis, which is a function value of 0. Part B, as x approaches negative infinity. So now, what's the function doing? As x approaches negative infinity, it's going out, out, out here. The function's getting closer and closer to the x-axis again, getting closer and closer to 0. Part C, as x approaches 3. 1, 2, 3. What's the function approaching? Well, from the left, it's approaching 1. From the right, it's approaching 1. Because the left and the right are both going to the same place, the limit is approaching 1. So part C's answer is 1. What about the limit as x approaches 1? Well, as we approach 1 from the left, the function is going to 1. And as we approach 1 from the right, the function is going to 1. The answer for part D is 1. Let me get out of full screen here. I'll pause this and get back to the notes. So now in the notes we're being introduced to the idea of a one-sided and two-sided limits. So far I've shown you the two-sided limits where both the left and the right have to agree. If both the left and the right agree, then we have a two-sided limit, and that's what's going to equal. But let me show you some examples in the worksheet where the left and the right might not agree, and you have to figure out what that answer is. So I'm going to go back to the worksheet again. So I'm going to pause, and I'm going to make it full screen again, and scroll up to example 2. We're going to do 2, 3, and 4 now. All right, determine the limits for each part of this function. So we've got limit as x approaches -2. Now notice it doesn't say anything up above the -2 as opposed to part B where it says -1 with a negative up in the exponent here. So this means it's a two-sided limit. This means it's a one-sided limit from the left. This is a one-sided limit from the right. So as we approach -2, so here's -2, from the left and from the right have to agree. They're both going to the same place. They're both going to 2. So the answer to example 2, part A, is 2. Part B, as we approach -1 from the left, we're going towards 1. So the answer to part B here is 1. Part C, as we approach -1 from the right, we're no longer going to 1. We're going all the way down here to -2. So part C, the answer is -2. Part D. Let's take a look at part D. Part D is a two-sided limit at -1. That means that the left limit and the right limit have to both agree. The left limit is going to 1. The right limit is going to -2. So the answer to part D is does not exist. And you can write DNE, does not exist. The limit does not exist. It's a famous quote from a movie. Part E. In part E, we're taking the limit as we approach 1. It's a two-sided limit from the left and from the right. as we approach the limit from the left and from the right, they're both going to the same place at 2. So the answer to part E is 2. Part F, we're approaching 3. X approaches 3 from the left. It's a one-sided limit. As x approaches 3 from the left, we get 1, 2, 3, 4, 5, 6. Looks to me like we are approaching 6 for the limit as we approach 3 from the left. As we approach 4 from the right, we're going to -1. And as we approach 6, let's go 1, 2, 3, 4, 5, 6. As we approach 6, it's a two-sided limit from the left and from the right. The answer is 0. That's example 2. Example 3. We're going to take a look at each parts of these. So, and this is the graph of this function here. X squared minus 3x over 3x, which would have a hole here at 0 because we can't have 0 in the denominator, so it's got this hole here. As we approach -3 from the left, we're approaching -2, so part A's answer is -2. As we approach -3 from the right, we're approaching -2, so part B's answer is -2. Part C is the two-sided limit. Since part A and part B both agree and are both going to the same place, then part C's answer is also -2. D, as we approach 0 from the left, we're approaching -1. As we approach 0 from the right, we're approaching -1. In part F, even though there's no value of the function here, for part F, the two-sided limit, because parts D and E both agree, they're both going to -1. So the answer to part F is -1. The answer to part G, what is the function's value at 0? Well, the function's value, if I put 0 in, is undefined, UND. Do not get undefined and does not exist confused. Functions are undefined, sometimes undefined. Limits sometimes do not exist. So part G is asking for the function's value, and that function value is undefined. Example 4. The limit as x approaches -2 from the left is 5. The limit as x approaches -2 from the right is 5. The limit as x approaches -2 from both sides, the two-sided equation, or two-sided function, limit, because they are both agreeing, A and B both agree, so the answer to part C is also 5. Part D, as we approach 2 from the left, we're approaching 3. As we approach 2 from the right, the function is approaching 3 again, which means in the part F, which is the two-sided limit, the answer is 3. What is the function's value at 3? Well, there's no holes here. The function's value at 2 is also 3, but it didn't have to be the same as the limit, as we saw in example 3. All right, that's the end of the worksheet. And I'm going to pause the video and go back to the skeleton notes. All right, let's take a look at example 8. Find the limit as x approaches 3 of the function 1 over x minus 3. Well, I can't do direct substitution because I'm going to get a 0 in the denominator. So let's take a look at the graph of what this looks like. So at 3, 1, 2, 3, we have an asymptote. And hopefully you remember from your Algebra 2 days how to come up with the graph of rational functions. So the graph looks like this. Okay, The x-axis is an asymptote. We have a vertical asymptote at x equals 3, and we have opposite corners here. We can graph this function. This is a two-sided limit, which means we need to check both sides. We need to check the limit as x approaches 3 from the left of f of x. I'll write it out of 1 over x minus 3. And we need to find out what the limit as x approaches 3 from the right of 1 over x minus 3 is. If these agree, then we will know the final answer, the limit as x approaches 3, two-sided, left and right, of 1 over x minus 3. Okay. So as we approach negative 3 from the left, as we approach 3 from the left, what's the function doing? As we get closer and closer to 3 from the left, it looks to me like the function is diving down here and going to negative infinity. As we approach 3 from the right, as we're approaching x equal to 3 from the right, the function's blowing up and going to positive infinity. These do not agree, therefore, the two-sided limit does not exist. D-N-E. Okay. Example 9. Limit as x approaches 3 of x squared minus x minus 6 over x minus 3. Again, I can't do direct substitution because if I put a 3 in here, I'm going to get a 0 in the denominator. If we look at this function, then we actually get a graph that looks like this. We have a graph of a straight line that has a hole at 3 because it's undefined at 3. And we look at it and go, but the left and the right limits are both going to the same place. Now we can find that algebraically by doing just a little simple algebra here. Limit as x approaches 3 of x squared minus x minus 6 factors into x minus 3, x plus 2 over x minus 3. And I can reduce the x minus 3's. Limit as x approaches 3 of x minus plus 2. Now I can do direct substitution of this function, which is the same as this function, just without the hole. And that equals 5 when we do the direct substitution. So that was example 9. Example 10. Again, let's see if we need to do any algebra to fix this. But as I look at this and I go, wait a second, let's not forget that direct substitution is an option if we can do it, but I can't because I'm going to get a 0 again. Always look to see if you can do direct substitution first, because that's what we did in problem number 5, I think. Yeah, way back in problem number 5, we were able to do direct substitution. We didn't get a 0 in the denominator. So we will get a 0 in the denominator here, so we can't do direct substitution. Let's see what algebra we can do. Limit as x approaches 2. This factors x minus 2, x plus 1 over x minus 2. X minus 2's cancel. limit as x approaches 2 of x plus 1. And now I can do direct substitution. 2 plus 1 is 3. Okay, sandwich theorem. Now, you might not see it when you open up this Google Doc. This is an Easter egg. It's a hyperlink to a video. So isn't this? So isn't this? These are links to a woman named Krista who does calculus problems. She teaches / tutors calculus on YouTube. She's been doing it for a very long time, since back when she was in college. Her videos go back a long way. She's introducing something called the sandwich theorem. What the sandwich theorem basically says is if we have one function, h of x, that we know is always above or equal to another function, f of x, okay, then we can sandwich these two functions around another function that maybe we can't find the limit of. So maybe I can't find the limit of g of x directly, but I know g of x is always in between h of x and f of x. Okay? G of x is never above h of x. G of x is never below f of x. It's always in between them. Okay, so we have this relationship here. Actually, the f and the g should be reversed. F of x is always less than g of x, which is always less than h of x. Sorry, that's a typo. Where g of x is always in the middle, no matter what. Well, at the value of x equals a, or x is approaching a, if the limit of f of x is L, and the limit of h of x is also L, then the limit of this g of x is L, because we know that the three have to be occupying the exact same place together. Okay, so let's take a look at example 11, where we're going to do, we can look at the graph. And how do I want to explain? Okay, so the function that we're taking the limit of is x squared times sine of 1 over x. I can't do direct substitution because I'd have a 1 over 0, which is undefined. Can't take the derivative. I can't even take the sine of something that is undefined. Okay, but the x squared function, this is the function that we're taking the limit of. It's got this hole in the middle here. But this function here, this wavy, curvy one, is this function right here. The x squared function is always above that function. It's never below that function. The negative x squared function is always below that function. Okay? How do I get that algebraically so I know which functions to look at for the sandwich? So we're going to do this. We know this relationship for sine. The domain for sine, the range for sine is always between -1 and 1. Sine is never bigger than 1. Sine of x is never smaller than -1. Okay, so the range for sine is always -1 to 1. Okay, this is kind of close to this function here. Okay, kind of. What about the range of sine of 1 over x? Well, it's the same range. I'm taking the sine of any numbers. This is all real numbers. This is all real numbers except for, can't put 0 in. The range doesn't change. Okay, the sine of 1/10 here is the same as the sine of 10 here. So this range hasn't changed. What can I do to this function to make it look like this function? Well, I can multiply it by x squared. X squared sine 1 over x. Well, if I'm going to multiply the middle by x squared, I have to multiply all three sides by x squared. So this is negative x squared. This is positive x squared, right? Negative 1 times x squared is negative x squared. Positive 1 times x squared is x squared. And these are the two functions that this function is sandwiched between. This is the negative x squared function. This is the positive x squared function. I can take the limit of the left function and the right function. Okay, I can take the limit, and let's write limit as x approaches 0 of negative x squared. I can do that by direct substitution. That gives me 0. I can take the limit as x approaches 0 of positive x squared. Again, I can do direct substitution. That's 0. The limit of this one is 0. The limit of this one is 0. This one's always in between those two. That limit has to also be 0. Okay, I'm going to write above here the limit as x approaches 0 of negative x squared is less than or equal to the limit as x approaches 0 of x squared sine 1 over x is less than or equal to the limit as x approaches 0 of x squared. This is 0. Less than or equal to the limit as x approaches 0 x squared sine 1 over x less than or equal to, this one is 0. This one has to be 0. It doesn't have any other place that it could be. So the limit as x approaches 0 x squared sine 1 over x equals 0. Therefore, okay, that is the answer to example 11. You have some IXL problems that you can work on, and here's the bookwork to work on. That's it. Thank you very much. Bye.